that we have that will take us from those pixels to the actual label, right? And we want to, the goal is of our network or our neural network, which we'll get into the structure of. The goal is to approximate that function, is to get as close as possible to a perfect function that will perfectly map from that image data to those correct labels that will correctly like match those true labels. And the idea of a neural network is that it starts off performing pretty terribly, honestly. It's just pretty like sort of randomly spitting out values. You'll give it an image and it'll just kind of randomly say it's a 9 when it's really not. But then it'll train. So over time, given those answers, those labels, it'll get better and better. And in the end, if it's trained correctly, that network will be able to see images of digits in this example, or just whatever the data is in whatever more general case. And it'll be able to perform that like prediction or classification or regression, whatever you're trying to do on that data it's never seen before. So it'll work on, data it's never encountered in training. So to get into the structure of how a neural network can do this, can approximate this complicated function, its most like fundamental small component is a neuron. And essentially a neuron is just some function that it has multiple inputs. And you can see here, in this example, it has 3 inputs, like just 3 numbers, like x1, x2, x3. And then it outputs a single number, which is like this y hat in this case. And it does this by taking in these 3 numbers, this x1, x2, x3, and then multiplying each one by some weight, which is just, which could be a different weight, W1, W2, W3 in this case, for each input. And you can see this exact formula here. Like it takes in some x's from x1 to xn in general. Maybe it's not just 3 inputs. And then it multiplies them each by an individual weight. And that's kind of saying like this input is more important, this input is less important. Like a high weight will be saying this this input will have a high effect, like a high impact. It'll have a high effect on the output. And it could even be negative. So it could be like inversely weighted, for example. But those are just some numbers. And then we have a B. This B here is a bias, which you could add. You add after doing all the like multiplications and like summing of the weights and inputs. And the idea is these weights, the W's and the bias B, are parameters. And what it means by parameters is that the model can change them during training. And what training is really just changing these numbers, which you can think of if you're thinking of like a big machine as like the function. It's just some like dials and knobs that we can change that will change exactly how the function like works and what the function is. And the idea is if we change these, if we have enough of these numbers, enough of these parameters, the overall neural network that will be able to replicate like any function, because it's such a complicated function that we just need to find the right values of all those parameters. And so that takes us to, if we want a really complicated function, we're going to need many of these neurons. So the idea is we arrange them in these layers where each of these like each circle is a neuron, and then the vertical line of neurons is a layer. And the idea of the layer is that each layer takes the inputs, right, before all those x1, x2, x3 from the previous layer, and then it'll send its outputs to the next layer. So for example, like see this neuron here is taking in the inputs from all 4 of these neurons, doing its math, multiplying by the W's, adding the B, the bias, and then sending its output, its single output to the next neuron. And actually, if we have time, we'll look at this later, but a single layer is mathematically equivalent to like a matrix multiplication. I don't know if you guys know much about linear algebra, but a matrix multiplication is just like a very common linear algebra operation. And computers can actually like really well optimize them. Like there's a lot of like study of how to make matrix multiplications really fast. So it can kind of do it all at once instead of just like individual multiplications and additions. And then the other important part is, aside from just the neurons and the layers, is that we have something called non-linear activations. And what that means is the reason why we need these nonlinear activations, which are essentially just functions that are nonlinear, not just a line, is that if we had just those linear layers, like just those neurons, which we call the layers of neurons we call linear layers, then actually the whole model would just be equivalent to a single linear layer. Because the idea is we have lines, like a linear function composed in a linear function like if you were to take these functions and put in another function, put in another function, it actually just decomposes mathematically to like one linear function, if that makes sense. Like if you could transform it multiple times, but it's really equivalent to just one like more complicated, different linear function. And so we need some nonlinearities to get some like curvature or like more complexity in there. Because so this image is showing that, you know, if we wanted like a regression model, which is a different type of model, that is like where those points are like the actual data, that's clearly following a nonlinear relationship. And so that line is a bad model, right? Because it and it could never be a good model because no line is really going to be a good approximation or a good regression for those points, because it follows a nonlinear relationship. So we need the nonlinearity because just a line or a plane in, you know, many dimensions, like called a hyperplane, it can't work for like really complicated functions that aren't nonlinear. And so this new image, this is called a ReLU. So this is an example of one of the nonlinear activations that's very common. And you can see, even though it's composed of lines, right? It's just like a horizontal line, like at 0, until you get to 0, and then it's just like X, right? It's just like a line with a slope of 1. Even though it's just like composed of lines, it's piecewise linear, but it's not actually linear. And so that like the fact that it's not linear means means that the function can take on like a really complicated shape. And so we'll use those after every neuron. We'll run the output of a neuron through this ReLU or another nonlinear activation. But ReLUs are very common. And that will give them the overall model. If you think of the model as just one giant function, it'll give that like some complexity. It's like some valleys and peaks, and so that it can approximate like nonlinear relationships. And another key important idea that will come into play is the idea of loss, which a loss function is just it outputs some number. So it takes the output of our model, and it can compare that to the true answer. And the idea is the loss is a measure of how bad our model is performing. So if the loss is like really low, like 0 is like typically the minimum, a loss of 0 would mean that it's performing perfectly. The output of the model is exactly what you want it to be. And a higher loss is bad. A higher loss, which typically loss can go up to infinity, means that our model is performing really poorly and its output is like really far from what we want it to be. So that would, connecting back to the digits, that would be like the actual label is a 2 and it thinks it's like something completely different. And it really is really confident that it's not a 2. Like that would be bad. And this is just an example of like a very common, this isn't really neural networks at all. This is just like linear regression, but it's similar to the idea of linear regression, if you're familiar with that at all, of least squares, like where you're just trying to minimize these residuals, these green lines. You're trying to minimize the square of those residuals. So basically, it's similar to that idea where you're trying to minimize some value. And that value is like how bad your model is. But the question is, you know, we've been talking about, we have this complicated function, but how do we actually train it? How do we make it? How do we know how to change those weights and biases, those parameters, to make the model better? And this is getting kind of into the weeds. This is getting into some calculus. And so if it's a little like too intimidating or you don't necessarily understand it, that's okay. But I think it's really valuable to understand like what's going on in a neural network. And we'll get into it in a little bit. I'll try and draw it out on the chalkboard probably, like the actual process. But the idea is something called backpropagation, which essentially just means we're going to have basically the tree, it's called an expression tree, which means every value in our neural network, like every output of a neuron, wherever it is in the network, whether it's like in the middle or toward the end, kind of knows where it came from, like what operation created it and what values went into that operation, and so how it was created. And so we can use calculus, which, you know, to calculate the derivative of the loss with respect to every parameter individually. And what that essentially means, right? It's, you know, the derivative is, if you remember from calculus, is essentially just like a slope. And it tells us, in this case, the derivative of the loss with respect to a parameter lambda means how the loss changes if we change lambda, that parameter value, a little bit. So for example, if that value, if partial L partial lambda was like 1, for example, that means that if we change lambda slightly, like if we increase it slightly, that means the loss will increase slightly. And so that tells us if we want to decrease the loss, then we want to decrease lambda. If that derivative was negative, then we want to increase lambda so that the loss would decrease. And also the magnitude of the derivative kind of tells us how much we want to increase it, right? Like if it's a really small magnitude, we would want to only increase, well, it actually depends. But we'll get into this, and that's something we'll get into in a second. But backpropagation is not how we change lambda, but it's just how we calculate first those derivatives. And we'll get into that. I'll draw that on the board at the end because it takes a little bit to put up the projector. But so I was hinting at it a second ago, but then what we do with the backpropagation, so we have those derivatives, but why those derivatives are useful is because that tells us how to move the parameters, how to change the parameters, as I was saying before, because during training, you want to change the parameters to make the model better, to decrease loss. And the backpropagation gives us the derivatives, which is really, the whole key to tell us how we change those parameters. And so with that formula on the left is telling us that we want to move every parameter lambda a little bit in the direction of its negative gradient. So the gradient is a concept from like multivariable calculus. So if you don't really know what that means, it's okay. It's not the end of the world. A gradient is essentially just meaning like a multi-dimensional slope, kind of. So in this case, we see like a 2-dimensional or 3-dimensional space. And the idea is we start off from like, if this is like our loss function, so this is not the actual like output of the model, but this is our loss function. And then like the inputs are our parameters. Like we have like thetas here, like theta 0 and theta 1. In reality, we'd have a ton of parameters, like thousands or hundreds of thousands or millions, maybe billions of parameters. So it's not so simple to visualize. But in this case, let's say we just have 2 parameters. In this case, we start off probably pretty high in our loss because we're just randomly outputting things. But the gradient, the fact that we can use backpropagation to calculate all those derivatives, tells us like how to change our parameters. So in this case, it's telling us like if this is our starting point, the backpropagation tells us that we should change the parameters a little bit, and that'll make the loss lower. And so we just kind of keep repeatedly doing that, making small moves each time. And eventually we'll be going kind of down this hill, right? And the idea is we want to get as low as possible because low means a low loss. So that's good. So the gradient descent, that L right there is just kind of what's called a hyperparameter, which just means it's just some value we choose. And that's called a learning rate, kind of telling us like how much we move each time in the gradient descent. So for example, like kind of the length of these like moves, that's the learning rate. A really slow learning rate is bad because it'll take us like forever to get out. Like we'll make a move and we'll barely move at all. But a really, really high learning rate is also bad because if we have like these terrain, right, of like valleys and peaks and things, a really high learning rate, like it might just go like way too far in one direction. Like if we started here, a really high learning rate might make us go like past this valley completely and go like way too far. So that's kind of another thing. Hyperparameter, how to find like the correct hyperparameters, because hyperparameters aren't being affected by or being trained by the network at all. How to find like the proper value of a hyperparameter is kind of, really complicated subject on its own. So we won't really be talking about that. So, like choosing that value, the learning rate, it's pretty complicated. And you kind of have to do it on your own because the model won't just like find it. And that's kind of everything for just the basics, at least for the slides. But I think I'll be talking about, I want to talk about a little bit of the math actually. So I'll be showing how this is a matrix multiplication. That's probably good. Oh, just kept going. So if we just have like just to keep the numbers small, can you all see that kind of? Yeah. Okay. So if we just have like a small layer of like 2 neurons, and then we have another layer of 2 neurons, and these are like all sending, their information like forward, we'll call like the value output by this neuron X1 and the value output by this neuron X2. So the output of this neuron, right, we'll call its first weight W11. This is not 11, it's 11. we're calling it one. The first one is because it's the first output neuron. It's this neuron instead of this neuron. And then the second one is because it's the first weight. So you'll see that as we write it out fully. So that's multiplied by x1, the output from this neuron, plus w1, 2. So it's still 1 because it's the first output neuron, but 2 because it's the second weight, times x2, and then plus some bias, we'll call b1. Right? Does that make sense? And then for this, the output of this neuron here, is its own, so it has its own weight, w, we'll call it 2, 1 now, times x1, plus w2, 2 times x2, plus its own bias, b2, because they can have their own separate biases, like it's different biases, possibly. And then this operation where like the x1 times this number, x2 times this number, x1 times this number, x2 times this number, that's equivalent to matrix multiplication. Do you guys know like matrix multiplication? No? Okay. Well, the idea is that we can just kind of write it in this way, and that's more efficient for a computer to calculate. It's really well, or they're good at optimizing matrix multiplications. And then that's times the x1. So the idea of a matrix multiplication, out here, you can read it. Just make sure. Is that the x1 and x2 will kind of like come over and like, so like these, the x1 and x2 will kind of distribute, and the x1 is multiplied by here, and the x2 is multiplied by this one. And that's like the first value. And then the biases, I haven't drawn the biases yet, is b1 and b2 is added after. So it's basically just a little bit of linear algebra, and a computer is good at optimizing. And then the other thing I wanted to talk about was, oh yeah, does it make sense when I say like a linear, because I could show it or I could skip it if we wanted to have time on the other things, that like a linear times like composed within a linear. When I say composed, it's like you do one linear transformation and then you do another linear transformation on the output of that, like the linear layers together. Does it make sense to you guys that like that is in itself just like one big linear transformation? Because I could write it out probably really quickly. Okay, I'll just do it because it's really quick. The idea is that if we had like the first one, like y1 is ax plus b, right? So we have ax plus b, and then we just have another transformation that's like, or I'll call this f. So this is like our first linear function, and this is our second linear function. And we'll call it cx plus d. If we compose it, like, so like f2 of f1, so like you just do, like the output of one of them becomes the input of the other. Then it's a times, now the input, this x here, is this whole function. So cx plus d. You can read it? Just make sure. Everyone can read this? Okay, good. Plus b. Then when you distribute this, it's a cx plus ad plus b. And this ad plus b is just like some other constant. And then this ac is just a constant. So again, it's just a constant times x plus a constant. And so that's just another linear transformation. So we need the linearity in there so that it's not just like one big plane. So you can have as many linear layers as you want. It kind of doesn't matter. It's just linear still. And then the other thing is backpropagation, and that's probably kind of the hardest one. But so the backpropagation, have you guys taken like Calc 3? Yeah, okay, good. So we'll just do a simple example. The idea of backpropagation is just that, like, so let's say we have these like two values, a and b, and we're going to multiply them, and that's just going to give us a loss. So this is like just a super simple like one operation kind of thing. So our loss is equal to a and b. like or A times B. The idea of backpropagation is that like we can calculate our partial derivative of L with respect to A. Can anyone tell me what that is? If it's A times B, what's the derivative of L with respect to A? Yeah, yeah, it's B. And so that tells us, so like when we're actually training the model, like A and B will take on specific values. And so like, let's say if B was like 4 and we want to decrease the loss, then we would decrease A, right? And the magnitude would tell us like how much kind of, or would affect how much. Because since remember when it's multiplied by that learning rate, a higher derivative will mean we move more in that direction, right? But the idea is also, this is kind of key. So I'll do the other one just to show off. So partial L with respect to B, partial L, partial B is A. And so that kind of tells us, how to move these like values. If we wanted to decrease L, that's like the derivatives tell us how to move A and B. But also if we had more values like before, like if A was an intermediate value and it was calculated by other like inputs, like C and D, like let's say it's C plus D gives you A, right? So A equals C plus D. Then with the chain rule, right? If we want to know how these values C and D will affect L in the end, we can actually calculate it kind of just with the intermediates. We don't need to go through the whole like process, and because the function is going to be too complicated to do all that. Like here in this case, we could write out like L equals C plus D uh, times B. But when we're with like a big neural network, it's going to be like way too complicated to write out the whole function. So we just do it in like steps. And so I'll show you what that means. So like so with a chain rule, we know, all right, look for a place. I'll write it over here. With a chain rule, we know that partial L, partial C, so like how will changing C affect L, is the same as partial L, partial A, so how A affects L, and then partial A times partial A, partial C, right? So if we want this like the overall derivative, how C affects L, we can just do it in like each step. We can just get the derivative from C to A and then the derivative of A to L. And so we already have this partial L, partial A. So if we just calculate like partial A, partial C, where A is equal to C plus D, can anyone tell me what that is? If C plus A equals C plus D, what's partial A, partial C? It's 1, right? Because it's just like D is ignored as a constant. So it's just like the fact that there's a 1 here and invisible. And so that means, so I wrote B here up here to say that partial like that's like the derivative of A, like that's how A affects L. Because we calculated that before. But then so C affects A with this value. And we can plug in like if we want this full thing, like how C affects L, partial C. And so we can calculate that by just plugging in the value of partial L, partial A, which we calculated here, B, times the partial value of partial A, partial C, which we calculated here with 1. So C also, it just since it kind of flows through A, it's also its derivative, like partial L, partial C is also B. It's derivative with respect to L. So you just like kind of multiply each step. And we could do that with, an arbitrarily large network, right? Like if we had a million like values before this, like a really big network. And of course the derivatives, the individual derivatives, like we just did like simple ones here, like A and B and 1. But as long as all your steps are like differentiable, like the ReLU, it's a little bit more complicated, but not that much, like because it's piecewise, or like a multiplication or, whatever operation you're doing, as long as it's differentiable, you can do this back propagation like many, many layers back. And that's how we get derivatives for like, a neuron like way up at the front, even if it's like many layers in the front. Does that make sense to everyone? Yeah. Yeah, so that's everything for the math side of thing. So we'll get into like actually coding in PyTorch. Just stop on its own. So have you guys used Google Colab before? Collaboratory? You know what that is? Okay, so if you can just open, so have you guys heard of Jupyter Notebooks? Jupyter Notebooks? Yeah, it's similar to that. It's like Google's version of it. It's like an interactive environment, which means, well, I'll show you. So you can open a new one by like going to Google Drive and then plus there's probably other ways to do it, but this is the way I always do it. And then opening new, and then it's under more, and then Google Collaboratory. Or if you can't figure out how to do that, you can just like follow along, like just watch along and kind of like pay attention. And the Google Collaboratory, the idea of it is it's similar to Jupyter Notebook, which is just that you have like these things called cells, and you can run code in each of them instead of just like running. So you don't have to run the full program like like you're doing it in like an IDE. You could just do like pieces of code individually. So for example, like it's just like Python. So if like 1 with A equals 3, like we can do that and then print out A. Hold on, you can see that. And then we can like run this part and it'll do it in like pieces. But anyways, so if we want to actually build our model, the first thing we do, this might be a little fast. I'm going to try and go like not completely too fast. But it might be better to just, if it's like way too fast, maybe it'll be better to just like watch and just try and understand. But so the first thing we need to do, and I think we'll share we posted the notebook in the meeting resources, right? Yeah. The full completed notebook is on the meeting resources channel in the Discord. So you could just look at that, I guess. But we'll be developing it here. So the first thing we need to do is make all these imports. And then I'm also going to show you guys, so you can run it by like clicking like this play button here, or you can click, I think it's like Control Enter. We'll like run it and Shift Enter. We'll like run it and move to the next cell. There's some little shortcuts for you. And so all this stuff is like PyTorch, all this torch. And so the reason PyTorch is really useful is that it kind of does all the stuff I was showing about like the backpropagation and the gradient descent. It contains obviously like the it can do that kind of itself. We don't have to worry about the manual backpropagation. It kind of does it itself. And it can keep track of all those values and like the gradients and the partial derivatives. So we don't have to worry about that. But also it's useful. It has really nice like kind of notation or syntax, just like NumPy. If you guys have ever used NumPy, like it's pretty similar. It's very similar in that we can do stuff like this where like, so this is like creating a range of values from like 1 to 10, so not including 10, so like 1 to 9. And also if you just put like a variable at the end of a cell and run it, it'll like print it. So this shows us it's a tensor, which is basically a type of like multi-dimensional list from 1 to 9. Oh yeah. Very good. Okay. And also like some other syntax that's really nice is that like we can do like element-wise operations with PyTorch. So I'll just try and get through this pretty quick, and then we'll talk about actually like building the model. So for example, like this is multiplying every element by 2 and then adding 1. Whereas in normal Python, we have to like loop over that, right? But here it just does it kind of on its own, like as if this was like a single value. But it's a whole, list. And we can also do, obviously like, multi-dimension is really important. So like we could do like another range. From 1 to 6, because the 7 isn't included. And then like if we reshape it into 2 by 3, and then this keyboard's like messed up. Oh my god, the enter key is like broken, and then a million new ones. I'll use the other enter. So if we print out X now, you can see it's like it's just like multi-dimensional, and that's stored in like this variable in shape. You can see it's 2 by 3. And that's useful because I need to convert this to floats. That's useful for some operations, like you can do like a mean, over a certain dimension. Like dimension 0 will give you like, what? Oh, I didn't run this. Oh, X equals X. That's converting the data type, so you can do a mean. So this is like doing it over the dimension. Like average of 1 and 4 gives you like 2.5, average of 2 and 5 gives you 2.5, and so on. And you could also do that over the other dimension, dimension 1. Get the other one. So that's why that's a little bit of PyTorch. But then now we'll actually build them up. So the first thing we need to do is just load the actual data. So we're doing that. We chose a nice way to do it. That sometimes it's more complicated. Like you have an actual file that you need to import. But here we have from this import of the Keras data sets, it kind of just has all the data just kind of there for you. And we're going to load it into separate categories. So we have X train, Y train, X test, and Y test. So the X versus Y, X means like it's like the image data, like all the pixels, and then the Y's are the labels, like what digit it actually is. And then the train is a data set, so it's just kind of like arbitrarily shuffled into train and test. So train is all the data that's the model's actually being trained on, that they'll see during training. And then the test is hidden away. That's kind of like the actual exam, so that after the model's done training, it'll run it on the test data and see how it performs on data that's never seen before. Because it would be kind of unfair. It'd be too easy if we tested it on data that's already seen during training. So that's all the data. And then we need to do some operations on it. I'm going to also copy paste this in. So, well, here, first I'll show you. X train, its shape is going to be 60,000 because there's 60,000 images, and then they're 28 by 28 each. And we'd rather have it like flattened out, like all the pixels just kind of flattened out in one dimension. So we're going to reshape them into this -1 just means tells PyTorch to like infer the value, and then 28 times 28 will just give us like the value, like the flattened value. It's like 784 something like that. And then also we want to have all these stored in Torch tensors so that we can do like the training on it, like the that send it actually through the network. Because originally it's NumPy, that's why this is from NumPy. When we load it in here, these are like NumPy arrays, and so we need to convert it to Torch, and then convert it to certain like the correct data type, so floats, and then the Y label should be like long with like integers. And then the other thing is the X data when it comes in originally. Here, I'll load it again. Is originally like 0 to range, the pixels each range from 0 to 255. And we'd rather have it like range from 0 to 1 because that's just like more numerically stable for the network. It'll train better. So we divide them all by 255 to turn it into like floating point values between 0 and 255. And now we're also going to have a little visualization thing. So I'm going to define this function. Actually, we don't need a whole function because we only use it a few times. So I'm going to just have, we can see the images. If you want to actually see the images, you can run plot.imshow and then run it on some image. Like let's say like let's just look at the first image. And again, we're gonna have to reshape this back to 20 by 28 because we flattened it before. And that'll show us in this weird color scheme. That's like what you use by default. But this is like a 5. And it's kind of a weird 5. And some of these images, it's actually kind of a hard task, but some of these images are pretty weird. That's a 5. Big break Y train. That's a pretty bad 5. So it's not surprising that a network like computer would have a hard time like reading, because that's a 5 right there. Yeah. So that's our data. That was like some of the training data, X train and the Y train. And here we're going to talk about the actual model. So the way PyTorch works is it's like each model is a class, or you can even define components that are a class, and it inherits from a torch class called a module. So it kind of inherits a lot of stuff from that. That's very valuable. So the first thing we're going to do, okay, I'm actually just going to copy paste it so I can talk about it, and then you can try and type it on. The first thing we're going to do is define our values, or structure of our model. So this supercall is just calling the super constructor like of the superclass. But these n in, n hidden, and n out are like the number of neurons that are going to be in each layer, right? So we saw before in the neural network that it could have like multiple layers of neurons. It's kind of something I guess, failed to emphasize that we have, multiple layers of neurons, and those neurons, the size of the each layer, and also the number of layers, kind of defines the complexity of the model, right? And something called, if you've heard of the term deep learning, that's because it's deep if it has like many layers deep of neurons. And so the input layer needs to be 784 because that's how many like pixels are in each image. It's 28 times 28. And then we're just using 1,000 because the width, I guess that's a good number. You generally don't want to like, send it to like a tiny, like if we only use like a few neurons, that would be like the more neurons means more complexity, more parameters for the model to use. But you don't want to use too many neurons because you don't want it to be like, overly complex because that would take longer to train. And also there's something called kind of overtraining or overfitting the data, which basically means we're just kind of memorizing the data and it doesn't actually perform well on data it's never seen before. And then the output, we're going to have 10 because that's how many digits exist, 0 through 9. There's 10 digits and we want to output like numbers that are going to kind of be our confidence level for each, like how much we think it's each number. So like a really high number, if we have like this tensor of 10 numbers, if we have a really high value in the first element of that tensor, that means like we're really confident it's a 0. And then we define these layers using this torch thing called a sequential, which basically just means we're going to be running the layers sequentially. Each output of like the layer's output will be fed into the next layer's input. And so they'll just feed into each other. And so first we'll have just this big linear layer, which is just that layer of neurons we talked about. And we're going to use like these values, the 784 and 1,000 are going to feed in, and that tells it how many like inputs it's going to take and how many outputs it's going to send out. And then we use the ReLU, so that doesn't have any parameters, it's just a function. It's just the ReLU function we talked about. And so that's the nonlinear activation. And then we have another linear layer that takes us from the 1,000 neurons to the 10 output neurons. And then we need to define a function forward. And that just tells us, like when the model will take in that data, like the image, so this X is just like the image data that someone will send in. And then it'll just run it through all those layers. And the layers will process it and it'll output the 10 numbers from this linear at the end. And that'll be like our prediction. So to actually like use the model, we just need to instantiate the class. So our class doesn't have any parameters, so we can just do it like that. And then we're gonna call the output logits. So I'll talk about that after I print it. So so we'll just send like the first image through the model. And then the other thing about PyTorch that's nice is that you can send like it kind of works with, because of the multi-dimensionality, you could send in one example or you could send in like multiple examples, like one image at a time, or you could send in like 1,000 images at a time, and it'll just kind of do it all in parallel. So the output, our logits, are just these values, right? That are arranged, they're not actual probabilities because you can see they're negative and they don't sum up to 1. They're just some values. But a negative value, we're going to interpret a negative value to mean like we're predicting it's not that number, and a high value means we're predicting it is that number. And when I say that number, I mean like the order it's in, like this is level of prediction for a 0, a 1, a 2, up to a 9. So it looks like here, it's just kind of, we just initialize the model. So it's just kind of like randomly outputting that it thinks it's a 1, it looks like is the highest value. When we saw before that the X train 0, was actually a 5. So it's just kind of randomly saying, right? So we wouldn't expect it to be good yet. And so one thing that's kind of cool is that we can see 2 things about the model, just like look at it, kind of examine it. So the first thing, this is kind of complicated expression. This is just summing up all the number of total parameters, and we have 795,000. So that's a lot, right? So we of course couldn't do that like this is not like linear regression. It's complicated. There's a lot of parameters, and that's why we need the back propagation, because you can't just do it like, least squares linear regression. We could just do it with like an explicit formula. Like you don't need any neural network. because that's only 2 parameters, or sometimes more. But here, so this line is printing the shape of each parameter. So this is like the first layer that sends like 1,000 to 784. Or actually, this is kind of reverse order, but like the 784, it takes in 780. It's a matrix of 1,000 by 784 like dimensions. And then we have the bias that's size 1,000, and then we have the second matrix for the second layer that's 1,000 by or 10 by 1,000, and then the second bias or the bias associated with that second layer is just 10 or size 10. It's like just 10 biases. And if you added all these up, like 784 times 1,000, like you could do the math, and that would come out to 795,000. But anyway, on to actually training the model. So we're first going to define this variable, which is just like the number of iterations of training we're going to do. And we'll say, actually, it's a little high, I'll say 10. And then we're going to declare another model, actually. And then we need something called an optimizer, which is going to do like the backpropagation for us. Or actually, it's going to do the gradient descent. The backpropagation is a separate thing. So we need to use this, like it's built into PyTorch. The SGD stands for, the GD of SGD stands for gradient descent. The S is stochastic, it's stochastic gradient descent. So we talked about, descending, like we started on that hill and went down and as low as possible in the loss function. So that's what this is going to do. And we need to give it all the parameters of the model. And then we're going to define the learning rate to be 1, just because that's a good value. You could kind of find that experimentally. You just kind of have to play around and find that yourself, typically. So we're going to do it max iter times. And then the first thing we're going to do is kind of reset the gradient of the optimizer. So that's called optimizer.0grad. That's just kind of resetting the gradients that's held by the optimizer. And we just kind of need to do that every time we do the backpropagation or the gradient descent step. And second, we're going to get the output of the logits just like we did before. And we need to calculate the loss from that. So I didn't really talk about this before, but the way we calculate the loss from the logits output is really, it's something called cross entropy. And that's just, this F is, remember, we imported this before and it's called an F, but it's just from PyTorch before. It's torch.nn functional. So it's just a function we imported that'll take the logits and also the labels. And the way that works is it basically just compares, it needs the labels because it'll look in the position of the correct like value. So like in this case, it would look at 5, like 0, 1, 2, 3, 4, 5. And this value it wants it to actually be high, right? So first it actually can compute from these logits, it can calculate, like, turn these into probabilities basically through this operation called a softmax, which we don't really have time to necessarily talk about, but it will convert these to probabilities so that they'll all be between 0 and 1, and they're all summed to 1. And then basically it'll calculate a better loss the higher the value in the correct position. So that, and that way the model will try and make that value higher in the future. Right, because we want the value in the correct position to be as high as possible. Ideally, we want it to be like 0s in all the wrong positions, and then a 1 in the position like the label actually should be. And then this loss.backward is doing the backpropagation we talked about. So it'll be like setting the gradient. So there's partial derivatives for all the neurons before, all the values before. And then we do optimizer.step, and that does the backpropagation. So that changes all the parameter values to be slightly in the direction of the negative gradient. That's the gradient descent. And then here we're just gonna do a little print to see our loss and see it like decrease over time. Hopefully it'll decrease if we've done everything right. And that might take a little bit to run. And yeah, so we can see our loss decreasing slightly. So what a good loss is, like in terms of absolute magnitude, kind of depends like on the context, but we just wanted to see decreasing. But yeah, sometimes we get this randomness in and it'll increase actually. That's not good. Yeah, and then sometimes it comes back down. this learning rate might be a little too high, but it did come down eventually from the original value. So to measure the actual, like, how good this is in a more human terms, instead of using loss, we'll use accuracy. So I'll use this function, calculate accuracy. And when I say accuracy, I'm just saying, like, what if we just made it predict on some value, like on it gets some images and we tell it to predict, like how many, like what percentage of the time does it get it correct? So again, we'll just compute output. So we're going to make this in general, so we could run it on the training data or the test data or a subset of that data. So we need the images and we need the labels. That's like the X and the Y. So again, we'll just compute the logits. And then for the predictions, we're just going to take the maximum. We're just going to take like the maximum logit. So that's what this statement is doing. And then we're going to say it's correct when we sum up. We'll sum up all the times the prediction is equal to the label. And you don't have to understand like exactly what all this PyTorch is doing, like why it works exactly. You wouldn't have to be able to write it yourself because PyTorch, it's pretty complicated, all these statements. Like it takes a little bit to learn. So I'm not expecting you to like be able to write this at all. And then the total number of images, we're just going to take that from the shape. And then the accuracy, or ACC, is going to be just the correct divided by the total number. And we'll return that accuracy. So that's a function, and we can calculate the accuracy of our model by passing in the images and the labels. So here we'll just pass in the entire training data, training data set, and the entire, like the X and the Y of the training data set. And we got 68%. So that's not very good, but we're going to improve it in a second. And also we could probably improve it by running like a little longer, maybe a lower learning rate, or like maybe changing the structure of a model, like adding another layer. But anyways, let's see what it is on, whoops. Let's change, we need to change that to test. And it'll probably be lower because the trained data set, it's seen it before. Okay, actually it's slightly higher. But if you were to train it like really well, typically the trained data set, like since it's seen it before and since it trains on it, it's typically it performs a little bit better on the training data set. So we got 68%. I think if we trained it a little longer, it would be better, but that might take a while. So we're going to do something a little better actually called batching. So up here, we were sending in like the entire XTrain, the entire data set of training data through the model all at once. And so each iteration, like each step of this for loop kind of took a while. And we only made one move, like this optimizer that step, we only made one step in that gradient descent. Each time we sent the entire training data set through. And so that kind of takes a while because it takes a while to compute all that, like all the calculations for the training data set and then also back propagate. And so so we only take like one step. We didn't do many steps. Since we only did 10 iterations, we only did 10 steps. And so we can do this better actually. And this if we do something called batching, which means instead of sending all the training data through at the same time, we're gonna like randomly sample from it, a small sample, and then send that through and make a step for the small sample. And so that way we can do a lot more steps. And we'll converge, we'll get a lower loss much faster. And here we're going to define batch size. So as I was saying, we're going to have batches of 32. That means we're only going to send 32 examples in at the same time, and then like adjust the parameters. Yeah. So that if you want to bring that back to the analogy like studying, that would be like you only look at a few problems at a time. You do all the math, like you do all your calculations, you do all your work, and then you look at the answer key, and then you adjust your brain and learn from it instead of. Whereas before, so that's batching. Before we were doing like a lot of questions, and then we look at the answer key and adjust our our neurons, our brain, which is more inefficient because it takes us so much work for us to make one step, for us to make one gradient descent step. So I'm going to copy paste in some of this. So again, we need to declare optimizer in the model. And then here we're going to do something called epochs, where an epoch is similar to the iteration before, where an epoch is measured as going through all our data. But remember, since we're doing through it in batches, we'll be doing it as in like, we'll look at 32 images, we'll look at a different sample of 32 images, we'll look at a different sample of 32 images, and it's sampled in such a way that the images don't repeat. And then once we've done so many samples that we've run through all our images, then we'll repeat again. And so the epoch is, a single epoch is like looking at all our images in batches. Like once we do one epoch, that means we've looked at all our images once, but we've done it in separate batches. If that makes sense. So we're going to define the lists to track some of the losses that we can look at the end. So similarly, we're going to do just a for loop over the number of epochs. And then we're going to define another variable called epoch losses. Just another list that we'll use to keep track of all the losses. But then the difference is we're going to do another for loop where we're going to loop, like where each of these loops is, this inner loop is over the batches, right? So XB stands for like the X of the batch, and YB stands for like the Y of the batch. And this loader that we use up here, the data loader, is doing all the batching for us, like doing the math of randomly sampling and doing it so that they don't repeat. And so that's very, very useful. And that'll be, so this X batch and Y batch, we can print the shape when we do it, but that's where we get like the 32. It's only going to be 32 examples at once because we define the batch size up here. So I'll copy it in piece by piece. So similarly to before, we're going to need to like get the output from the model on running it, but now instead of running it over the entire X-train data set, we're just doing it over the batch. So that's going to be a lot faster because it's a smaller data set. There's only 32 images instead of like 60,000. So it'll be faster. But each of these iterations will be faster than like this long iteration before where we're passing in the entire training data set. And then again, we need to calculate the loss. We need to do the zero grad. This time the order is a little bit different. We're doing the zero grad a little later, but as long as we do it before, we calculate the backward here. It doesn't matter like necessarily. So it doesn't really affect anything. And then again, we're going to adjust the parameters with the optimizer step. And then we're going to use these lists that we defined before and append the loss to it. And we'll print that and graph that to see how the loss decreases over time. And then after we've done the batch iteration, we're going to calculate the mean loss of that like epoch, right? And that'll give us a kind of an average and a more smooth average. And we'll see that in a second, that some of these losses are going to be really noisy. But if we like average it out, overall the loss is still decreasing. Yeah. Oh, okay. But yeah, we're almost done. We might run a little over. But this training will run probably a lot better. And yeah, so you can already see after one epoch, because the difference is we're doing each of these steps, we're doing it one step per iteration of the batch. So a single batch, we do one step. We look at a batch, we do one step. And so that means it's doing way more steps. And technically, because we were looking at a batch of 32 and then adjusting all the weights, the gradient is technically not as accurate because the gradient is just dependent on batch, which might be like slightly biased. Like it's not necessarily a representative sample, but it works out and it's still advantageous because we do so many of those iterations that even though we might be going slightly in a different direction than the true gradient, we'll still like find our way. So we might go in slightly the wrong direction, but it's still we'll do so many of those iterations that it's still better. So we got a much lower loss this time, 0.07. And so now if we can go back up here and just run it again, the accuracy is now on the training data set 98%, and on the test data set it's 97%. Right, that's really the core. So we kind of pretty much almost right on time, 7:28, 7:29. I still do have more to show if anyone wants to stick around, but obviously like the batching really helped. Maybe we could have done in more iterations that would have gotten it like with with this original training loop, maybe lower than 68%, but that was a really fast get to 98% and 97% on the test data set. So that's pretty accurate. One technicality that I'll talk about is that really the fact that we're doing this on images, right? On the images of digits. So we just did a linear layers for our neural network, but technically there's a type of like component of a neural network called a convolution that's actually more fitting for like images. So convolution instead of just a linear layer would be more fitting in this case for like image processing, but it's a simple enough image, like it's a small image. So the linear layer works out fine. But convolutions are kind of another subject, so I'm not going to like get in explain like fully what they are, but just know that like for different tasks, you use kind of different types of neural networks. And for images, technically, a convolutional neural network would be a little more fitting. But one thing I'll show, which is pretty cool, I think, is something called CUDA, which is NVIDIA's like platform to use GPUs. Right, so a GPU, so I'll explain what that means. So a GPU is a graphics processing unit, as opposed to a CPU, which is like a central processing unit. And that means GPUs are essentially a bunch of little cores, like many little cores, where a core is like kind of its own unit that can do its own processing. So CPU, so you'll hear like they're often multi-core nowadays. They might have 2 or 4 or 8 cores, but GPUs could be like hundreds or I think thousands of cores, and they're smaller individually, like less powerful. But the way a GPU works makes it really advantageous for neural networks. And that's why, I don't know if you guys know, but NVIDIA's, become really valuable financially because of all of the AI stuff, because they're really valuable to, like, if you're an AI company, you need GPUs because we trained all this on a CPU, just like a typical like chip. But a GPU would be a lot faster. And if you had a more complicated network with like more parameters, the CPU would just be like unfeasible. It would just be way too slow to train. And a GPU is like essential. So yeah, it's 7:30. So if you need to go, that's fine. But I'll just keep talking if anyone wants to stick around. So this device right now, we're declaring a torch.device, and that's like the device it's running on. So Torch can automatically detect if CUDA is available. And that's just like the GPU. So if we run this right now, it's just a CPU, right? We can only run on the CPU. But if we want to use a GPU, which we can use for free with Google, with some like amount of limited runtime, like you can't just use it however much you want. I think there's a limit to it. You can just go to runtime up here and then change runtime type. And then here it's CPU. And if we click here, we can use the GPU. And we click that and save. So that means, oh, what? Okay, so I won't be able to show it, but just like I was saying about the limits, I ran into my limit, I guess, and I didn't realize that I used too much. But yeah, I didn't know that. Oh, I did not know. I haven't even been using that much recently. But I was just going to show you guys. I'll just paste it. I'll just show you, I guess, the CPU version of it, and then tell you what using the GPU would look like. Oh, I need to do that. Back to CPU. So we're using a CPU, and then this will we're going to use this installation to time our cells to show you that a GPU is like way faster. And by the way, GPUs originally they're for graphics, and that's why it's like graphics is in the name. But the reason they're particularly suited for neural networks is because, as I talked about the matrix multiplication, it's kind of similar to graphics in that graphics is all about like a lot of the time you're doing one operation to like a bunch of numbers, like it's called single instruction multiple data, where you might be taking like a bunch of pixels and multiplying them all by 2, like something like that. And GPUs are obviously really good at that. They're built for working with like a big, matrix of pixels, like a big 2D grid of pixels. And so matrix multiplication is kind of a similar operation. Yeah, so if we were using the GPU, by default, these tensors are created on the CPU, and then we'd have to move them .2, and then dev is like the device. But because dev is a CPU, it actually doesn't, I can't use the GPU. It's not really doing anything. So this is still CPU. if we could use CUDA, we would be able to get this to say CUDA. But anyways, this at is doing matrix multiplication. And so for 5,000 by 5,000 matrix, those are big matrices. But again, as I talked about before with the layers, a matrix multiplication is just like doing the layers. And we did a layer with like 1,000 by 74 by 784. That was the size of one of our matrices. So 5,000 by 5,000 is not at all like out of the realm of possibility. We could have much bigger easily. And that took 3 seconds for just one of those multiplications, which you would need to do a lot of if you were doing like many, training. In training, you're sending like a whole batch at least. We did in the small, when we did a small batch of 32, that was quick. If we did a batch of 60,000, like the full training data set, if that takes 3 seconds for each of those, that would take forever. So that's a matrix multiplication, and I can't show it, but if CUDA was available, this would take like 100 milliseconds instead, like way faster in terms of factor. Like, what is that, like 30 times faster? And then that difference, that factor of speed, if we increase the size of this, like made it 10,000 by 10,000, it would increase even more. The GPU would still be like, I think when I tested it, it was still like close to 100 milliseconds. Like it barely increased if we were doing 10,000 by 10,000 matrices. But if we were doing on a CPU, it would take like 15 seconds or 20 seconds or something like that. But yeah. I think that's pretty much all I got. So that's everything for today. If anyone has any questions, you want to ask anything?